I'm Yuri Shinohara, an associate professor at University of Electrical Communications. My expertise is in metallography and crystallography. Our research focuses on martensitic transformation and non-diffusive crystal structure change in metallic materials. Here is the martensitic transformation of iron as example. Austenite transformed to martensite upon cooling. Martensite reverse transformed to austenite upon heating. Martensitic transformation can be used in wide industrial applications. For example, nickel titanium alloys are used in shape memory alloys. Deformed shape memory alloys back to their original phase by heating. Martensite formation in steel strengthens material, so martensitic stainless steel are used for high-strength fasteners. Here are the microstructure of shape memory alloys. Martensite plate forms triangle, zigzag, and hexagons. The question of our group have why martensite forms these morphologies. This question is also industrially important because the microstructure is closely related to their shape memory and mechanical properties. However, conventional crystallography have limitations. It primarily focusing on the interface between austenite and martensite, which cannot determine the specific morphology formed. For example, three morphologies shown here have the same austenite-martensite interface. We solve this problem using kinematics in addition to crystallography. The validity of the theory is tested using electron microscope, which are powerful tool for observing morphology and obtaining crystallographic information. By combining theoretical analysis with experiments, we can obtain information of the martensite-martensite interface. This information allows us to perform advanced analysis of martensitic microstructures. Now I present the result for iron-based shape memory alloys. The mirror indices at martensite-martensite interface were derived from theoretical analysis. We found the presence of a misfit at interface. Misfit is considered to be unfavorable for martensitic plate pair formation. So theoretically favorable morphology was determined using austenite martensite and martensite interface, and the condition that misfit is small. Candidate morphology was narrowed down to the three types shown here: sphere, wedge, and kink. We investigate whether the theoretically favorable morphology are formed in the observed microstructure. This is a crystal orientation map of the martensitic microstructure of iron, nickel, copper shape memory alloy. It can be seen that martensitic plates are formed in large quantities. Martensite was extracted from this map, and how many each morphology appeared was counted. Nearly 2,000 pair was analyzed to obtain accurate results. We found that theoretically favored morphology, namely sphere, wedge, kink, accounted for more than 70%. Furthermore, 3D morphology can be considered for a martensite plate cluster that combine martensite plate pairs. The three cluster morphology formed by sphere, wedge, kink pairs are shown here. In microstructure observation, the sample surface is observed. Namely, the cross-section of the cluster is observed. So we created a program to simulate the shape of the cluster cross-section. Kinematic theory shows that misfit is introduced when the diamond cluster forms, while misfit is cancelled for the other two clusters. In other words, the diamond cluster accumulates the misfit of sphere and kink. Misfit accumulation in diamond cluster has considered unfavorable for formation. Microstructure observations show that the diamond cluster formation was suppressed. This result allows us to discuss cluster formation from the perspective of misfit. Finally, we succeed in misfit visualization in observed microstructure. These are martensite plate pairs with a small and significant theoretical misfit. This pair has almost no misfit at the martensite interface. In contrast, the misfit is present for the pair with significant theoretical misfit. The misfit decreases away from the interface. Our group is working on cutting-edge metallographic analysis based on theory and experiment. In the future, we plan to clarify the relationship between martensitic microstructure and mechanical properties. We need the cooperation of researchers from various fields. We always welcome collaborative research, so please feel free to contact us. Thank you very much.